present you. Well, it's a pleasure for me to present our today's speaker, Wissam Elь Hadj. Wissam is a graduate student from the University Lyon 1 in France. So Wissam will tell us today about inflammation. This is inflammation propagation modeled as a reaction-diffusion wave. I will say a couple of words very shortly, but maybe Wissam, I will just tell me whether you are going to say something general about inflammation or you go directly to your topic. I mean, that it is, in fact, in many diseases, there are these inflammatory processes and the importance of that. Okay, let us do it like that. I think that you know this topic very well, maybe even better than I know it. So you might start, if you don't expect to do it anyway, you might start saying a couple of words about inflammatory diseases, that it's kind of a generic situation and so on. So please, you can start your presentation.
Thank you, Professor. First of all, let me thank the organizers of this seminars for letting me present today my work entitled Inflammation Propagation, Modeled as the Reaction-Diffusion Wave. This work was done under the supervision of Professor Vitaly Volpert and Professor Nader El-Khatib. Generally, to start a bit about inflammation. So what is inflammation? It is very general, but I will give a short definition and then try to explain a bit more about how important and how crucial inflammation plays a role in our body in general. So inflammation, first, the physiological process. It is a normal and integral part of the healing process and refers to the response caused by injury to the living tissues. It is also a defense process which consists of recognizing and removing dangerous or external stimuli. Inflammation, thus, can be considered as an essential defense mechanism. During inflammation, several cellular and molecular processes are mobilized in order to restore homeostasis and to resolve inflammation. Actually, inflammation plays a major and crucial role in many inflammatory diseases. For example, I will state several diseases that most of us know, like atherosclerosis, Alzheimer, multiple sclerosis, even asthma, eczema, skin diseases. If we want to name all the diseases, we're gonna not end today. But so far, this is actually one of the interests that guides us toward this work, that since inflammation really plays a major role in most of the diseases, how can we model it mathematically? So this was one of the insights behind this work that I'm going to present today. And this was a general introduction about inflammation so far. And now, for sure, during this presentation, I will go more into the details of what we are working on and give several regimes of inflammation in a future step. So to start our presentation, I will go through the table of contents. Today, during this presentation, I will start by a biological explanation, followed by describing the model. Secondly, or subsequently, I will proceed by an analytical study of the model, where we're going to focus on studying the stationary points, an analysis on the traveling wave solution, and then to provide different regimes of inflammation propagation. Then I will go through numerical simulation to show you some numerical results of our study. Last but not least, I will go through a discussion where we're going to differentiate or distinguish between the regimes of inflammation and provide a biological interpretation. But before starting the presentation, I forgot something. I would like to thank as well Dr. Anastasia Muzokhina for all the technicalities and help that one made during this week to make this the process of the presentation going well until now. Okay, thank you. So let's start now with the biological explanation. So since we have gone through inflammation in general, about what is the role that inflammation plays in our daily life or in our body in general, I will go through a bit about the inflammation process actually we are interested to study. I will start by a general representation or graphical, and then I will go through the really what to a scheme which describes exactly what you are modeling. So now it is just a general overview or a brief introduction about the process. So we start if you do have, as you can see in the mouse, here we have a set of cells that are uninflamed, that are not activated, that are normal cells performing their role naturally. Then for a certain reason, as you can see here in red, one cell is activated, or it is called inflamed cell. Since once a cell is inflamed or activated, we do have the production of pro-inflammatory cytokines and other inflammatory mediators, as you can see in red. And we have this inflammation propagation, as you can see in the arrows in red. Then the inflammatory cytokines, as you can see here, will attach on the external receptors of other cells, which will cause their activation, as you can see here, and they will be inflamed cells. I will go through in a bit more about the details of activation and so on. Again, here it's just a general overview of the process. And then, since other cells are activated or inflamed, we do have the recruitment of macrophages, or in general, immune cells, to the region of inflammation. Hence, an immunity reaction is set up. So now, what actually are we what are we actually modeling in our work, and what actually we are really focusing on? Here, I'm presenting it through a scheme that depicts the biological phenomena of inflammation. So in general, we have tissue. Once they are activated, they produce inflammatory cytokines, as you can see. The production of inflammatory cytokines will cause the activation, as you can see by this loop, of additional tissue, which will in return, again, produce inflammatory cytokines. The presence of inflammatory cytokines and other inflammatory mediators will cause the influx of immune cells. Specifically, we are considering macrophages, which will in return produce inflammatory cytokines. In general, this is the this is the biological phenomena that actually we are interested to model it mathematically. So since I have presented a little bit through the scheme, the processes that we are gonna study, I can now move to describing our model. So here we are considering 4 key players as explained. We have uninflamed cells, inflamed cells, I, M being macrophages, C being inflammatory cytokines. The first term here, alpha UC, models the transformation or the activation of uninflamed cells by the action of pro-inflammatory cytokines. And this term is present in the first and second equation. We also have the term beta I in the second equation, which models the death of inflamed cells. The death of inflamed cells can be through several biological mechanisms. I will go a bit into details and a bit about what is the different processes. The term delta I and Kc, both of them models the recruitment of macrophages due to the presence of inflamed cells and inflammatory cytokines, respectively. The term gamma 1M models the natural decay rate or the death rate of macrophages. The term here, as you can see, is the diffusion term, where D being the diffusion coefficient of cytokines. The terms B1I and B2M models the production of pro-inflammatory cytokines by inflamed cells and macrophages, respectively, and gamma 2C, the natural decay rate or death rate of inflammatory cytokines. Since we have gone through the description of the model and the several maybe terms of the model, I'm gonna jump into the explanation, short biological brief explanation about several terms, which are alpha UC and beta I, which is alpha UC being the activation of tissue. So as we have said, an inflamed cell or activated cell can produce inflammatory cytokines. Inflammatory cytokines can be, we have several inflammatory cytokines, example interleukins, interleukin-1 beta, or tumor necrosis factor like TNF-alpha. I'm not gonna go into naming them all. However, once a cytokine can bind to the receptor, to the respective receptor on the cellular surface of another non-inflamed cell or non-activated cell, we have this binding that happens. Once we have this binding between the receptor and the cytokine, we do have a activation of several intracellular pathways. Here we can name the JAK-STAT pathways, the NF-kappa B pathways, or the MAPK pathways, which will cause the alteration in gene expression in the nucleus of this non-inflamed cells, which will activate it. And by the process of activating the cell will cause the production of pro-inflammatory cytokines. Then as we have said here, a cytokine can activate a cell and will in return cause the production of more inflammatory cytokines. For the term beta I, which is the death of inflamed cells, here we have to differentiate between or to distinguish between three types of cell deaths. We have apoptosis, necroptosis, and pyroptosis, as you can see in the scheme. Generally, apoptosis, one of the main physiological process is cell shrinkage, which will cause the apoptotic bodies, the formation of apoptotic bodies. And then we have the process of phagocytosis. But before going into distinguishing between the three types now, let's recall that inflammatory cytokines like TNF-alpha can trigger the cell, can trigger the programmed cell death, which will cause either the death by apoptosis, necroptosis, or pyroptosis. The main difference between apoptosis, as you can see here, which is the last stage is in green, compared to the other two, which is in red, is that in the literature and by several biological literature studies or reviews, they considered that apoptosis, the final result of apoptosis, is considered anti-inflammatory or an inhibition for the inflammatory process. In contrast to necroptosis or pyroptosis, where the last stage of this type of cell death is considered as a pro-inflammatory or promoter of inflammation. As a physiological process for necroptosis, one main characteristic is cell swelling, where we have the disruption of plasma membrane and of the nucleus, which will cause all the elements or all the intracellular elements will go outside of the cell to the outer cellular space, and they are released outside and many of these cells are considered to be dangerous, like damage-associated molecular patterns or cytokines, or even many other dangerous molecules, mitochondria, or that are present in the cell. For pyroptosis, the physiological process is cell swelling and membrane blebbing. We do have, as a result, pore formation and the release of dangerous signaling molecules. Majorly, I'm not gonna name as we have named in necroptosis, but I can add here that you have the activation of precursor inflammatory cytokines, and which will cause a release of more pro-inflammatory cytokines. So now, I guess I'm done with this biological overview, and I'm gonna start by studying analytically our mathematical model that we have proposed. So we can see again the model, and I'm gonna start by studying the stationary points. In the study of the stationary points, we consider first the concentration of U being the concentration of uninflamed cells to be U0, and we study the kinetic system in order to find the stationary points. For sure, I'm not gonna go into the calculations. I'm just gonna say here that we have a unique stationary point found, which is E0, where the U0 is the concentration of U, and 0 being the concentration of all the remaining three concentrations, cytokines, macrophages, and inflamed cells. Since we have interested not only on finding the stationary point, but on looking at its stability, we are considering the Jacobian of the kinetic system, and more specifically, we are looking at the eigenvalues. Even more specifically, we are looking at the sign of the real part of the eigenvalues to check whether this point is stable or not. So I'm not gonna go through the work on the mathematical analogy behind finding this the eigenvalues, but I can say that we are we get into solving this third order degree polynomial in terms of lambda, where lambda is the eigenvalue of the Jacobian matrix applied at E0, where A, B, and C in that case are a combination of parameters. For sure, by several analytical methods, we get the following table, which summarizes the stability of the equilibrium point E0 with respect to our parameters. For example, if this set of parameters, gamma 1, gamma 2 minus B2K is less than or equal to 0, the equilibrium point is unstable. If gamma 1, gamma 2 minus B2K is positive, but bounded by this set of parameters that I have just highlighted, it is unstable. But if it's bigger, this gamma 1, gamma 2 minus B2K, bigger than this set of parameters, the equilibrium point E0 is stable. So now we are done with the study on the stationary points, especially on the stability of the stationary points. And now we are interested, since we are modeling inflammation propagation as a reaction diffusion wave, so we have to start by the existence of traveling wave solution. So to do that, we have started by a reduced model where we consider the parameter beta is equal to 0. Biologically, what does it mean beta is equal to 0? Simply, we are neglecting death of inflamed cells. Actually, several studies in the literature have performed the following assumption in order to study their models. So when we have applied this condition, that is parameter beta set to be equal to 0, our system of equation turns into a system of three equations with I, M, and C, inflamed cells, macrophages, and cytokines. And now for the system 15 till 17, we have a property which is very important, that is this system is globally monotone. What does it mean? Simply the Jacobian, the element of the off-diagonal element of the Jacobian matrix of the kinetic system of 15 till 17 is or all positive, which indeed gets us that to say that the system is globally monotone. Thank you for several theorems that are present in the literature, and we can say that in the monostable case, we can prove that there exists a constant C star, that for all C bigger than C star, there exists a traveling wave solution of velocity C connecting the two equilibrium points of the system. So in that case, we can prove, since we do have a monostable system, we can prove the existence of traveling wave solution. But if you recall, in our case, we do not have diffusion terms in all of our equations. And this theorem applies in the case where we have positive diffusion coefficients. However, thank you again for several studies. As you can see here, I have cited an article that state that even though several diffusion coefficients are equal to 0, we can still prove the existence of solution. And I will not go through the proof, but I have cited it in order to let it be clear for everyone that this study was made, and the general result, one of them, is that even though several diffusion coefficients are said to be 0, we can still prove the existence of solution. Since we have proved the existence of traveling wave solution for this reduced model with beta is equal to 0, we are looking now for the C star, or for the minimal wave speed, or for the wave speed of this traveling wave that we have proved the existence. So for this case, we follow a method that is used in the literature by simply introducing a new change of variable, where xi I can call it, which is x minus ct, as you can see. So we define v, w, and z in terms of x minus ct, or xi, and to be equal to I, m, and c respectively. By doing this change of variable, we get the system 19 till 21. And since we do have to get limits for v, w, and z, and the two limits of v, w, and z are taken to be the equilibrium point or the stationary points concentrations respectively. And here we do only impose that this denominator is positive and indeed bigger than 0. To go now to the analytical estimate of the wave speed, we consider the solution of the form, as you can see in this, I'm highlighting now, P1 E minus lambda x, P2 or P3 E minus lambda x. I will not go for sure through what is the analytical study and how do we do it, but in general, the work is when replacing V, W, and Z by the following form, and then by excluding the values of P1, P2, and P3, interpolating them or interchanging them, we get finally to see that the minimal wave speed C star is the minimum of a function f of mu, as you can see here, where mu is bigger than mu0, where mu0 is a positive root of the denominator, as you can see in equation 25. Similarly, we go back to the initial model, which is the complete model, and we perform the similar analytical study on the minimal wave speed and so on. So here again, we consider for the initial, we consider the same change of variable xi, which is x minus tt, and we do the following change of variable to obtain the system 26 till 29, and we impose the limits to be 0 for v, w, and z, and for u at minus infinity is uf, and at plus infinity is u0. What is uf and u0? U0 is the initial concentration of uninflamed cells that is considered to be known and constant, and UF being the unknown final concentration of uninflamed cells. Here I can note that this concentration is unknown. Now, to get the minimal wave speed for our problem and for our complete model, we go through considering U is equal to U is equal its value at plus infinity, which is U0 as an approximation of U. Following the same analytical method by this change of variable and by interchanging the values of P's, we can get that C is the minimum of a function f of mu, as you can see here, where mu is bigger than mu0, where mu0 is again a positive root of the denominator, and as written in equation 34. So now we are happy, we have obtained the analytical estimate of the wave speed, but since we are working on modeling, so why not comparing it with the numerical wave speed of the system? So what we have done, we have considered a set of value of the parameters, and we have considered one special parameters, as you can see here, which is B1, as an interval found biologically in the literature. So again, let me recall that B1 is the rate of production of inflammatory cytokines by inflamed cells or by activated cells. So we have found this range of value in biological literature, leading us to varying this parameter B1 for several values of the parameter for a fixed set of parameters 3 times for 3 different values of B2. So here in the scale horizontally, we have the value of B1 from 0.005 till 0.1. And we have here in the horizontal line the wave speed that is obtained numerically and analytically. For the curves, you can see that the green curve is for a fixed value of B2, which is 1.5. The yellow is B2 is equal to 2, and B2 and the red curve B2 is equal to 2.4. I'm gonna zoom a bit maybe so that you can see better that we have 2 curves actually. The green, red, and yellow are the one which is the analytical wave speed based on this set of parameters, and in blue the numerical wave speed based on the set of parameters. Here I can note that you can see that they are coincide, which leads us to say that our analytical estimate coincide with the numerical value obtained of the wave speed. So now, followed by the study on the numerical and analytical wave speed comparison and maybe analysis, I'm gonna go through another topic that interested our analytical study, which is the final cell concentration. Here we go back to the model where we did the change of variable by x minus ct or by xz. Here, what we have done, we were able to integrate each of the 4 equations and to exchange the integrals subsequently to get the equation 39. But since equation 39 is we have a lot of parameters, we have opted for making it a bit easier to see, where we introduce the and I think as seen in equation 41, the parameter omega, where omega is the ratio between the final concentration of uninflamed cells over U0, the initial concentration of uninflamed cells, and R being this combination of parameters. Here I can note that R will be defined to be an inflammation number, the inflammation number, since our study in the next part of this presentation is really based on the value of R. Since we do know that equation 41 has a solution in the interval omega 0 between 0 and 1, if and only if this inflammation number R is bigger than 1. So now, when we have in the case that R is bigger than 1, we do have this we have that the equation 41 has a solution. We can find the value of UF, which is the final concentration of uninflamed cells, and in addition, we can find the final cell concentration of cytokines, inflamed cells, and macrophages. So now, since we have introduced the famous inflammation number R, we can state that the stability of our stationary point E0 can be translated in terms of the value of R, simply by the table that we have obtained previously where we were studying the stationary point and its stability. This can be translated to the following definition based on R. So if R is less than 0, or if R is bigger than 1, the equilibrium point E0 is unstable. However, if R is between 0 and 1, the equilibrium point is stable. So now, one of our main interests that was very interesting for us, that the value of R can be negative, even though parameters are all taken to be non-negative or positive. So here, what we are taken to be non-negative. So here, what we really made us think a bit more that why we do have this combination and what is the behavior of the solution in that case. Actually, in the literature, studies really did not consider this case because we do not consider its negative values. But however, here, as you can see in the denominator, we have a difference between gamma 2, gamma 1, and B2K, that even though all these parameters are taken to be non-negative, this combination can be negative, leading to say that R is negative. So we have proposed, in order to explain the behavior of such case and of such solutions, we consider the case where we take I is equal to 0, which means that our maybe biological insight behind taking this decision or scenario is that after a subsequent time or after enough time, all cells, inflamed or uninflamed, are gonna die, since we consider that by the parameter beta I, all terms are gonna die, and we are left at the end by M and C, which is macrophages and cytokines. This was actually the biological insight behind this proposition. So we are left with a system of two equations for M and C, where we're gonna look again on the kinetic system and more specifically on the stationary point. The stationary point here is E1 is unique and is 0, 0. Looking again at its stability, so we are using again a similar method that we have used previously, which is looking at the Jacobian of the new kinetic system. We can state that if this combination of parameters is negative, the equilibrium point is unstable, and if this set of parameters is positive, the equilibrium point is stable. Simply here, we're just gonna state that when this is negative, we know when this set of combination is negative. This case correlates with when we have our R, or the inflammation number, which is negative. So here, this suits our interest and gives us a more into, does it really explain what we're gonna have in this case where R is negative? So here, I'm not spoil the result, but I have opted to just give a small biological explanation of this condition that maybe will sound interesting, and maybe will give us a more reason why we do have this case, and why we do have that. What does it mean to have gamma 1, gamma 2 minus B2K is less than 0? By the definition of our parameters, we know that we can say that when this combination is negative, which means that the rate thus of immune cells and cytokines is less than the rate of production of recruitment of macrophages / cytokines. Sorry, production of cytokine recruitment of macrophages. But for now, I'm not gonna go a lot into this biological explanation. I have just opted to say that this reduced, or this decision on taking this reduced system made us a more explanatory behavior of the solution, especially in the case R is less than 0, where we do have that this set of combination of parameters is negative. So now, since we have gone through the analytical study of the model, we're gonna jump to numerical simulations. For numerical simulations, we clearly do need a set of parameters. So we have opted, as you can see in the first table, that a set of parameters that mostly are taken from the literature, and you have kept only two parameters, as you can see below, that are varying in order to cover all the cases that you want to study, and R is less than 0, R between 0 and 1, and R bigger than 1, recalling that R is the inflammation number. So the method used in our case is implicit finite differences, where we consider the initial concentration of uninflamed cells to be 1, or the initial concentration are taken in red. I'm gonna zoom a bit when I wanna explain, but here, just to explain that here, the initial condition are taken in red. For uninflamed cell, the concentration is 1. For uninflamed for macrophages and inflamed cells, here it is 0, the initial concentration. And for inflammatory cytokines, we consider a jump function, as you can see here, at let's say like between 0 and 1 of the interval, where the interval is taken between 0 and 5. So again, the method here used is implicit finite differences, and I'm gonna go to explain a bit more what happens. So if you're gonna go to this figure of uninflamed cells, the initial perturbation of the system was made by inflammatory cytokines between 0 and 1. So here, as you can see, followed by this initial perturbation, we do have a front wave that propagates, as you can see, as the mouse is moving. From the initial concentration of uninflamed cell, which is 1, until stabilizing, as you can see, they are moving on that way with subsequent times. The concentration of uninflamed cells is changing over time until stabilizing at a final concentration, as you can see here in green, which stabilizes at a final cell concentration, or called UF. Here I can note that UF approximately the value is 0.13, and this value coincides with the analytical value we have obtained in that case. For example, for inflamed cells, an initial perturbation in the concentration of cytokines again leads to a front wave that propagates, as you can see here, at subsequent times. We do have this front wave that propagates with time until stabilizing at the final stage at the value 0 in green. Similarly, for macrophages, I will try not to be too repetitive, but just to make it clear that an initial perturbation of cytokines leads to the formation of this front wave that propagates with time until stabilizing in green, as you can see here, at a 0 concentration for macrophages. Similarly, for cytokines, here I'm really not going to be repetitive. Maybe I have said it 3 times, but again, here we have this front wave that propagates with time until stabilizing at a final value, which is 0 concentration of inflammatory cytokines. For the second case, which is the case of R between 0 and 1, here, again, we are perturbing by the initial concentration of cytokines, similarly as in the previous case. But here we can note that this initial perturbation of in the concentration of cytokines does not lead to a front wave that propagates, which means that that does not represent an inflammation propagation. As you can see here, only the final concentration of uninflamed cells in green is on the wall interval capped very close to 1 here in the region of inflammation, but here it stays exactly 1 in the remaining part of the interval. For inflamed cells, here maybe you can see the red initial concentration of inflamed cells, it is 0, and it goes back to 0 after shortly after the initial perturbation. We do have this going back in the concentration of inflamed cells to 0. And similarly to macrophages and cytokines, this initial perturbation of cytokine does not lead to a front wave that propagates, and we directly have this attenuation until reaching a 0 concentration of cytokines, macrophages, and inflamed cells shortly after the perturbation of the initial condition. The last case, which is the case R is less than 0. This case, as I have said previously, is very interesting and suits our interest in several studies where we, especially in the analytical and now in the numerical part. Here again, the initial concentration of uninflamed cells is taken to be 1. For inflamed cells and macrophage is taken to be 0. And for inflammatory cytokine, a jump function between 0 and 1. Here we can note that after the initial perturbation in the concentration of cytokines, we do have this front wave that propagates, as you can see here, it's going in that way at several subsequent times until stabilizing at a value of U, which is equal to 0 in green, which is the final concentration of uninflamed cells. For inflamed cells, similarly, the initial perturbation in the concentration of inflammatory cytokine does lead to this front wave that propagates, as you can see here, with several times, until stabilizing at a final time at a 0 concentration of inflamed cells. For the concentration of macrophages, and surprisingly, this initial perturbation by cytokines does lead to a front wave that leads to, as you can see, a final concentration, which is a huge number compared to 0, which was the initial concentration of macrophages. Here we can note, similarly, we have this similar shape. It's increase in the values in the case of inflammatory cytokines. Here I may note that here maybe due to the scaling, the value of inflammatory cytokines at the end is near 0. But however, if we zoom or if we really do study in a more, if we increase this maybe the size of the figure, we can see that no, the values are increasing over the whole interval. What is interesting in that case, that the final concentration of inflamed cells or uninflamed cells is 0 in that case. So we do not have any more cells that are activated or not activated as well. But the concentration of macrophages and cytokines are increasing, and dramatically, even I may say exponentially increasing, as you can see in the figure here. So we have this accumulation on the concentration of macrophages and cytokines. Here, for sure, a question will come up to your mind. Maybe I have said that we have a front wave, like in figure A or B, and I said the same thing for C and D. However, you told me that we are not able to see this front wave. So this is why we have opted for the following explicative or informative figures, where we have taken 3 consecutive times, T1 in red, T2 in black, and T3 in green. Here we have noted this front wave that propagates between T1, T2, and T3 for concentration of uninflamed cells. Similarly, we have for the same time, at the similar point interval, if we look, we are on the same interval in space, we have this change in the concentration of inflamed cells. But in the concentration of macrophages, which I was explaining previously, that if we do maximize or if we do zoom, we can see this propagation and this accumulation in the concentration. Here you can see that around x is equal 1.6. We do have an increase in the concentration of macrophages and in the concentration of inflammatory cytokines. If we look at the right of the figure, the concentration of cytokines is still equal to 0, which means that we still do not have a propagation on the right-hand side. But on the left-hand side, when here the concentration of inflamed cells has reached 0, or it is decreasing in the case of the inflamed cells towards 0, we do have an increase in the concentration of inflammatory cytokines here on the left side and of macrophages. Then this proves, or this clearly gives more an insight or a better understanding of what is happening, that we do not have more inflamed cells. Inflamed cells or uninflamed cells are not present anymore. Their concentration is equal to 0, but the concentration of macrophages and cytokine is increasing dramatically or even exponentially to higher values. So we can state here that you have an accumulation in the concentration of inflammatory mediators, mainly macrophages and cytokines, which plays a major role in our immune system. So here, times to start our discussion, where again here I'm distinguishing between the 2 types of inflammation that we have, where we have an inflammation propagation. First, I will state the case R between 0 and 1. If you recall, we did not have an inflammation propagation. We don't have a front wave that propagates. Then it is a regime of inflammation. It's called a non-inflammatory case, but we're not gonna go into it now, because what really suits our interest is this different mechanism that you have between the case R bigger than 1, where we have this front wave that propagates, but the final states, as you can see, are 0 for inflamed cells, cytokines, and macrophages, and for the case R less than 0, where we as well have this front wave that propagates, as proven here, but the final concentration of macrophage and cytokines is increasing dramatically or exponentially on all the interval. So here you are able to differentiate or to distinguish between the 2 regimes. The first regime is called regime 1, which is the case R bigger than 1. Here we can say that the inflammation is mainly led by the interaction between I and C. So here we can say that we have tissue, they are activated, they have produced cytokines, and we are in this loop. So this loop here, this loop of inflammation actually is leading the progress of the front wave here. Because at some point where we do not have any more inflamed cells, the concentration of all inflammatory cytokines and macrophages is reaching 0, and the concentration of uninflamed cells or tissue that is not inflamed is stabilizing at a final cell concentration. However, in the case of R is less than 0, we have noticed something very, I will not say strange, but that suited our interest, that we do not have any more inflamed cells, nor uninflamed cells. So no more cells are activated and all inflamed cells are dead. So there is not anymore a stimuli of this inflammatory reaction, but we do still have this accumulation in the concentration of macrophages and cytokines, which leads us to believe that this is a second regime which is led by the immune system, which is led actually here, inflammation is led by macrophages and inflammatory cytokines, which is this loop. As you can see, this loop is guiding the inflammation propagation, and in the case R is less than 0. In contrast, for the first case, R is bigger than 1, this loop where I'm putting my mouse is leading the inflammation or the front wave propagation in the case of R bigger than 1. Since now we have went through the 3 cases or the 3 regimes of inflammation, the non-inflammatory one and the 2, where we have this inflammatory regime or this propagation, I'm gonna go to again to what we are focusing on from the beginning, from the title, as we have seen on all over the slide, that is inflammation propagation modeled as a reaction diffusion wave. And when we are talking about reaction diffusion wave, we are really interested on as well on the minimal wave speed, or on the wave speed, or on the speed of this wave that is propagating. In the case of R bigger than 1, we do have that where we have presented at the beginning this comparison between the numerical and the analytical wave speed. We have obtained based on a biological interval for the parameter B1, recalling that B1 is a production of inflammatory cytokines by inflamed cells. We do have a range of the wave speed, which is ranging from 0.006 millimeter per day to 0.1 millimeter per day. Here I can note that this correlates with, here in the first one, with B1 have the lowest value, and here B1 has the higher value based on the interval we have obtained from the literature. Here, why I am stating that, maybe what numbers are not very accurate in that case, but what I can say that the proposed model that we have proposed actually give us a generic representation of the speed of propagation of various inflammatory reactions. For example, in the case of atherosclerosis, if you have recalled at the very beginning in the introduction, I have talked about inflammation, atherosclerosis. Inflammation and atherosclerosis can take years or even decades to propagate, which leads us to believe that maybe this value of, which is considered maybe 0.006 millimeter per day, can coincide or can describe a generic representation of the speed of propagation for this type of inflammatory reaction in atherosclerosis. But however, in the case of skin diseases, where we all know that inflammation is way faster and directly on your skin, all of us had maybe skin diseases, we do have the spot that is growing within a few days. This value of wave speed, maybe to 0.1 millimeter per day, can give again a generic representation of the inflammation propagation in the case of skin diseases, or maybe in other inflammatory diseases that are considered faster or more faster than inflammation, atherosclerosis, and so on. This leads us again to believe or to state that this model can give a generic representation of the speed of propagation of various inflammatory reactions. And surprisingly, for the case of R is less than 0, where we have just explained that we do have this front wave that propagates before this accumulation in the concentrations of macrophage and cytokines, that for several values of K's, where we have found, and again in the literature, we got a wave speed that is faster or more faster than in the case R is bigger than 1. Here, K is again the rate or the recruitment rate of macrophages based on the presence of inflammatory cytokines. We weren't very surprised that when K is increasing, we do have an increase in the wave speed. Again, the role of K in that case being a role in the immunity system, which is in this loop, which is the recruitment of macrophages by inflammatory cytokines, exactly these 2 arrows here, leads us, we are not surprised that when K is increasing, the more recruitment we have, the more this propagation, the more this inflammatory reaction is happening, and the more interaction between macrophages and cytokines happening, leading to a higher or an increase in the wave speed in this case. Now we have gone through the mathematical part, analytical, numerical of our model, and now it's time to start by the biological interpretation. We have stated our study based on the inflammation number R. What is the biological interpretation of R bigger than 0, less than 0, between 0 and 1, bigger than 1? Here comes our discussion on this biological interpretation. So in the case of R being positive, we have stated, as you have recalled in the formulation of R, that this is based on this, that this parameter is positive. The set of parameters, which is gamma 1, gamma 2 minus B2K, is positive. What does it mean biologically? Even though I have spoiled you before during our analytical study a bit about this biological insight, but here we can say that this condition can be interpreted as it does that the death rates of macrophage and cytokines are larger than the recruitment or production rates of macrophages and cytokines. Here, the death rates of the immunity cells, macrophages, and cytokines, we do have more death than the production/recruitment. Here we can say that in this case, whether an inflammation propagates or not, the final state is a non-inflammatory state since the concentration of I, M, and C reach a final concentration of 0. In the case of R positive, we have to distinguish between R less than 1 and R bigger than 1. When R is less than 1, E0, the initial stationary point, is a stable equilibrium, and here we can state that even a large perturbation of the non-inflammatory case, where we do have 0 concentrations of I and M, does not lead to an inflammation propagation, and the disease state returns back to the non-inflammatory state. This case is called a non-inflammatory state since we do not have a front wave that propagates that corresponds to an inflammation propagation. However, in the case R bigger than 1, this case biologically corresponds to an acute inflammation. Simply, the inflammation propagates until reaching a point where the concentration of I, M, and C become equal to 0, whereas the concentration of U reaches a final concentration UF. If you recall on the numerical figures, I'm gonna go just to make it more clear. The final concentration of inflamed cells, macrophage, and cytokines is equal to 0 as seen in green, but here the final concentration of uninflamed cells stabilize at the value of UF at a final concentration, which coincides with the analytical value of UF we have obtained, as you can see in green. Going back to our biological interpretation, here we can know that the final stage of this inflammation corresponds to a healthy state, simply because the concentration of I, M, and C becomes 0, and U, being the uninflamed cells, the tissue that is not activated, that is non-inflamed, is stabilized at a level called UF, at a value called UF. And the last case is the case R is less than 0, where this case corresponds to the condition gamma 1, gamma 2 minus B2K is negative. Biologically, this means that the death of macrophages and cytokines is less than the recruitment production rate of macrophages/cytokines. Here, simply, if we look at the balance, that we have the production of cytokines and the recruitment of macrophages overcomes the death rate of macrophage and cytokines. So maybe we do have this recruitment and production more than the death, leading to this maybe called deregulation in the immunity system. And this actually correlates with the instability of the inflammation-free equilibrium E0, since this point is unstable, as we have seen, and analytically and numerically as well, that this we have set at this point, but you are diverging towards higher values in the concentration of macrophage and cytokines. So this condition, or this biological insight for this condition, gamma 1, gamma 2 minus B2K, we can call it maybe a deregulation in the immunity system where no danger is sensed. We do not have any more inflamed cells, but we do have this this hyperactivation of the immunity system. Hence, we do have production of macrophages and recruitment of macrophages and production of cytokines. Even though we do not have any more stimuli, the inflamed cells are all dead. We do not have any more maybe at the tissue level, we do not have any more this inflammatory stimuli, but our body or our immune system is hyperactive. We have an extra production of macrophages and cytokines, and this can be interpreted biologically by several researchers and by the literature by what is so called a cytokine store, which means we have this hyperactivation of the immunity system, which takes role in, especially in autoinflammatory and autoimmune diseases. Our system senses a danger that is not maybe present, and we have this recruitment of macrophages, production of cytokines, and this reaction of the immunity system, even though, again, maybe the danger is not sensed anymore. And here I can say that the final stage of this case is an inflammatory state because the concentration of inflammatory mediators, either macrophages or cytokines, is increasing dramatically. Last but not least, since I have went through the biological interpretation and the model and so on, time to conclude. So what actually we have I'm gonna say simply that the highlights of our work. Thank you for maybe reaching at this stage of all this biological insights and analytical study. So what we have done so far, we started by developing a mathematical model for inflammation propagation based on PDE of reaction diffusion type. We studied the progress of inflammation as a traveling wave, where we studied the traveling wave speed of inflammation. We were able to characterize 3 different regimes of inflammation depending on the inflammation number R, and our model provides a generic representation of the speed of propagation of various inflammatory reactions. And now, thank you for reaching the stage, and I would like to say thank you for your attention.
Okay, thank you, Wissam, for this presentation. We have some time to discuss, and I would like to open this discussion asking you to show the model, please. In fact, I don't remember whether we discussed it before or I just thought it now, that in this equation 8 for inflammatory cells, and then you explained it very well on the next slide, that the death of inflamed cells, maybe you show the next slide. I think it was the next slide also. This one, yes, this one. You explained it very well that death of inflamed cells can be stimulated by these inflammatory cytokines. You confirm?
Yes.
Good. Then the question, if the death of inflamed cells is stimulated by inflammatory cytokines, why don't you write this term in this equation? Why death of inflamed cells does not depend on the concentration C of inflammatory cytokines?
Well, this is very interesting question.
Thank you very much that you appreciate my question. I'm glad.
Asked it previously, so this was very interesting. I guess maybe we can add it in that case, but maybe for simplicity of the model, we have considered to take in only beta I to be the general death of inflamed cells, not only to consider this reaction of cytokines. Maybe
No,
this.
okay. There are different mechanisms. You can, well, I will tell how I understand that. Well, to be biologically consistent, we should take into account, like you can say it, generic cell death, which is beta I, as you write it here, but we add also this cell death stimulated by inflammatory cytokines. So you write minus whatever you call it, beta 1 I times C. Okay. So why you don't consider it in this model? So one of possible, explanation, which is not very biological, but from the modeling point of view, we want here to develop some analytical methods, what you showed in your presentation. And these analytical methods, well, basically there are 2 of them. To calculate the speed of propagation, it can be done, but to calculate all these integrals, it cannot be done if you have this additional term in the equation 8. So, truly speaking, I don't remember whether this question was discussed in the paper or not, but what we discuss now is that beta, in fact, in equation 8 should be written in the form beta 0 plus beta 1 times C. This analysis you do here, you say that beta 1 is small, and we neglect it in comparison with beta 0. So somewhere it should be somehow explained. Do you understand what I say? So the next work you prepare now, again, the model you showed in our discussions, I don't remember whether you have this term in these new equations or not.
No, but I will make sure to add it now.
Yes, please do that, because I think that this is important to be consistent in this model. Okay, this was my first comment. The second comment is that you certainly know that we do some studies of viral infections where we do some, well, not exactly the same, but some similar analysis. So when we study these viral infections, we have three main parameters which characterize viral infections. We call it virus replication number. In your case, it is similar to what we call inflammation number. Then we have the speed of propagation, and we have viral load. By the way, I think that here you did not show the value of these integrals, no?
No, I didn't.
You did. Okay. So we know it, and we largely discussed it in these papers on viral infections, that the speed of propagation correlates to virus virulence. Do you understand that? This is important. Why it is like that? Because well, not we, but in literature, they have it what they call virus plaque assays, right? It's cell culture where they put virus and they see how the viral plaques grow. So growth, according to biological data, growth of this viral plaques correlates with virus virulence. But mathematically speaking, growth of viral plaques is determined by the wave speed. So we say the wave speed correlates with virus virulence. This is important. So in your case, you talk about the wave speed, but you don't give biological interpretations of the wave speed. So think, please, of course, no, it's not a question for now, but to think about possible interpretations of the wave speed in the case of this inflammation. For example, if you talk about skin diseases, there are these plaques, inflammatory plaques. So the size of these plaques depends on the wave speed. So again, in viral infections, there is a very clear biological interpretation, because in the biological literature, they use this notion of virus virulence. I don't think that in inflammatory diseases there is something similar. But I think it's a good point to think about. Maybe we can introduce something, I don't know how to call it, not the virulence, but something different, but something which biologically, not mathematically, but gives biological interpretation of this speed of propagation, right? Okay, I understand that. Similarly, in respiratory viral infections, infectivity what is infectivity? How fast disease is transmitted from uninfected individuals to infected individuals. For respiratory viral infections, we know that this infectivity is proportional to viral load in the upper respiratory tract. And viral load, it's exactly these integrals. Well, not these integrals, but similar integrals in the model for viral infection. Again, think please about possible interpretation of these integrals, because this integral, in your case, it determines the total amount of inflammatory cytokines and the total amount of inflamed cells. Whether it is possible to give a relevant biological interpretation of these quantities. You understand, yes, what I say? Okay. Okay, I'm sure Anastasia has some questions or remarks, but I will finish with my one last comment. In fact, of course, yeah, I already mentioned that that we study these viral infections, they're spreading. Also, viral infections with inflammation. This is important because Anastasia works on that exactly. Now, that viral infection is accompanied by inflammation. Okay, this is just a remark. But what, in fact, I did not think before, at least I don't remember, and probably we did not discuss it with you. Okay, we discussed several diseases which for which inflammation plays an important role, and you mentioned like Alzheimer's disease or some other disease. But what you did not mention, it's cancer. And I don't think that we discussed that. But this is very important in cancer. Inflammation is very important in cancer. So I think that, and I'm sure that there is some literature about that, including modeling literature. But since you study in detail all this inflammation and inflammatory diseases, I think that we need also to take a look at cancer from the point of view of its interaction, tumor growth with inflammation, because again, we understand from all that inflammation is very important. So, and certainly it is present during tumor growth. So how it acts, like stimulating tumor growth or down-regulating tumor growth? I think it's a very complex question, and probably it depends on many things. My assumption is that it can be both, depending on situations. But what I really suggest you, but you should not spend too much time, because otherwise, you can spend a month reading literature about cancer and inflammation. No, in your leisure time, you can read something about cancer and inflammation. Okay, I stop on that, please, if there are other questions or comments. Anastasia, do you have questions, comments, or anything to say?
I have some technical questions.
Yeah, please.
Could you please show the slide when you compare the numerical wave speed with the analytical wave? You said that the colored curves are the analytical wave speed, as I remember. And yes. As I remember, the analytical wave speed is the minimal estimation for the wave speed in the model. So for the numerical wave speed also, but here we see that numerical wave speed lesser than the analytical one. Could you please comment this?
Yes, thank you for this question, Anastasia. Yes, numerical wave speed was shown to be less than the numerical wave speed. Maybe I might note that we have this numerical error when we do implement some numerical methods. We do have this where we maybe consider some numerical issues that leads us to this change in the values of the wave speed numerically, because when you are working numerically, once we are working numerically, it's not analytically, we assume that we have errors, and maybe the error of this numerical methods is shown maybe here in that case, and this difference, I will say small difference in the value between analytical and numerical wave speed.
Well, I would like to add something about that. When we say that analytically we obtain the estimate from below, in fact, well, we say that because we want to be mathematically precise. But in fact, we do obtain the exact value of the wave speed. Not an estimate, but the exact value. Even though not always we can prove that mathematically, but we do obtain by this what we call linearization method, we do obtain the exact value of the minimal wave speed. Not always, it can be different in some cases, but in this case, we do obtain that. So why do you have the small difference? This is, as you said, due to the numerical accuracy. If you will increase your numerical accuracy by decreasing like space step, for example, you will. And I think that in some cases you verified that you have this convergence to this analytical value. So here the small difference is related to numerical accuracy. So this is a small detail, but please make sure to be precise about that. This, about this minimal wave speed, whether it is exact, whether we obtain it exactly or not, whether we can prove it mathematically or not. These are a little bit different questions. But here we do obtain exact value. This linearization method gives us exact value of the minimal wave speed. Why we can say that? Because in some, not in this case, but in some other cases, we can prove that. First argument. And second argument, because you showed for some set of parameters convergence of this numerical wave speed to the analytical wave. Okay, this is what I wanted to make clear.
Thank you. And can you also show slide 30?
13.
30.
30. Yes.
Yes, this one. I would like you to clear some points in this. The green line for the macrophages and inflammatory cytokines, are these the end value? I mean, if you calculate for the further time, does it grow further
Yes.
to the infinity?
Yes, thank you for this question. Yes, if we do increase the time, we do have an additional accumulation and the concentration of both inflammatory cytokines and macrophages. It will be increasing more and more. But for clarity of the figures, we have considered where the concentration of uninflamed cells and inflamed cells reaches 0. We consider to make it at least clear where we can see the initial concentration and the final concentration. To see this, maybe this, as you can see here, the black lines are increasing in size. But yes, if we do increase the time, we do have a more and more accumulation of both key players, macrophages and cytokines.
Thank you. And the next question, you measured the wave speed in this case. Also, what is the wave speed in this case? This is for the waves which are for uninflamed cells and inflamed cells.
Yes.
Am
Yes.
I understand right?
Yes, exactly. If you want, the method here is like the typical method. We do consider, for example, we draw this 0.5 line and we consider these 2 points, and we know the difference between the space and the time to get this wave speed numerically for this case. R is less than 0. Yes, we got the values that I have explained, that I have presented for this case are found numerically.
Okay, thank you. And maybe about the how can wave speed can be interpreted for the inflammation. Maybe I have some idea to discuss. One of the manifestation of inflammation is the redness. And for example, if we consider inflammation on the skin, we can correlate the wave speed with the area of red skin which grows in time, or something like this, at least on the body surface.
Yes, we can call it virulence of skin diseases, right?
Virulence. Maybe it has some medical term.
Yeah, this is what I asked Wissam to think about, how we can correlate with some, well, whatever biological or clinical characterization of diseases. Maybe they have some name for that. Yes, I'd like to return to this previous question asked by Anastasiya and your answer, Wissam. Maybe I forgot something. You say that in this case, which we see on the screen, you find the wave speed numerically. But what about analytically? Do you find it analytically?
Well, no, I didn't. But when I was trying to get for this case, and I have changing the parameters, surprisingly, we do have this minimal function where we do have. It has something to do, but it's not the shape of the function. If you want this minimal, is not anymore like this. I don't know if I can.
No, it's not. No. Okay, it might be different. No, it's not exactly the same, but okay, show please slides. I think it is 31. This one. You see, it's like the previous one, but zoomed on the previous one. Could we make it bigger a little bit? Yes. You see, it's not necessarily for you to measure here the wave speed if you do it numerically, considering the uninflamed cells, for example. You can do it also for macrophages or cytokines in these figures, because in the same way they move in space, you see. And in fact, these two variables determine wave propagation in this case. So if you return to your model of two equations for cytokines and macrophages, two equations. You don't write it as differential equations. No, so write this model in like partial differential equations. Look for solutions in the form of propagating wave.
Okay.
You will have the wave speed, and you look for this value of the wave speed, for the minimal value of the wave speed, for which you have monotonically decreasing solution. It will not be a bounded solution. It will be exponentially growing solution, but still you will find the minimal wave speed for which you have this positive monotonically decreasing solution. So you use the same approach. Equations are a little bit different, but approach, the idea is the same. You look for this positive decreasing solution, minimal wave speed for which there is this positive, and you will obtain the value of the wave speed. In fact, I don't know, maybe I forgot to tell you before. Try to do that. You will find the wave speed and you can compare it with this numerical value. Well, everything I tell you, I can forget 5 minutes after that, but I hope that you will not forget, that you know that at some point you will tell me the answer. Okay, good. Other questions? If no other questions, thank you again, Vissam. We stopped for today. Anastasia, could you recall, please, what is in our program? So, I mean, the next seminar, when you have, not the next week, in 2 weeks, right?
Yes, we skip the seminar in 2 weeks, and the next one is will be at May 25. It will be Ratus Alexander Sergeyevich overview of mathematical models of therapy of malignant cells.
It's the whole month we will not have seminars because we have different holidays. Then I will be traveling during about 2 weeks. Okay.
We can, if we very would like to, we can find someone to May 11.
Okay, I don't know. Anyway, it's all for today. Thanks to everybody. Have a good day. Goodbye.